क्या है उसका नाम? फ्लैश है? पेन ड्राइव में तो पड़े हुए हैं यार। अच्छा बन्नी।
नहीं, कल यहाँ से मैं हटवा दूंगा।
हाँ।
लगाएंगे, सिस्टम इतना कंजेस्टेड हो गया है।
ना बैठने में होगा ना काम करने
So
में।
you're planning to do and then we will.
अल्लाह कर लो।
You can finish down below. You can.
ये काम है, ऐसे करेंगे। इसकी बेल बज रही है, कौन बजाया? शो द हिडन फ्लैग।
अब तो मैं चार करा था, मैं फोटो चला रहा हूँ, तो चार नंबर वो चला रहे हैं, 3 नंबर दोनों डाल चलाते हैं, वो चला रहा है। पहले मैं कल तो निकला, मैं कल बहुत आ रहा था, एक्सेल बना रहे हैं,
चल। अरे कैमरा कहाँ है?
मनीष बेटा टीवी वाले बोलते हैं।
भाई कुछ खाली कर दूं? ये किस किस ने क्या?
चाइनीज लोग आ रहे हैं, ये कोई धंधा नहीं है, क्या तुम पढ़ा कर
भाई ये बताओ भाई, ये कहाँ गया इसका सेटअप? यही है ना? है? ये
Recording in progress.
क्या है यार, कौन है? भाई
So why we have created room in the lower
सीडी वन मेरे पास क्यों नहीं है?
and created above the sphere. So the reason is if you look at this one,
रतुल, ये एनडीआर केबल कैसे जलेगी यार? अरे वो कह रहा टाइमर में बेल बजानी है यार। हैं? इंस्टॉलर के बाद क्या आता है यार ये? हैं?
concentration in this period of temporary concentration, including CO2, methane, and on the right-hand side, it shows the change of the Earth's magnetic field. So the change of the main strength that we
Hello, anyone hear me?
Yes, ma'am.
Yeah, can you promote Vanya Jordanova? She is the chair of the session.
Okay.
Thank you.
Most welcome. ये कौन है वीना?
Hi, Gijun. Can you hear me?
Yes, Martina.
Oh, hi. Okay.
Hi.
Hello. So we will be able to share our screen, right?
I don't think so. I don't have the permission here. I think the moderator will do it. Start.
Oh,
my- Okay. So there are two moderators here. They will help, but I don't have the permission.
okay.
There's
Because I
no-
don't know, should I have uploaded my talk? How am I going to share the slides?
I was just got the permission from the host. Hello.
Oh, now I
Now,
see
yes.
you have
Yeah,
permission.
yeah,
Yeah. Okay.
yeah,
Perfect. Perfect. Okay.
So Vanya is still in the attendings. So hello, can you promote Vanya as well? Vanya Jordanova, she is waiting. Please. Hello, Vanya.
Yeah.
Must be really early for Vanya. It's 7 a.m.
Can
here.
Do you hear me now or no?
Yeah, we can hear you.
Okay, let's see.
Hello.
Hi, Vanya.
Yeah.
I'm actually in Bulgaria.
Ah,
Oh,
So
that's
okay.
why you have the sunshine in the background.
That's a little bit better.
yeah, a little bit better than 5 a.m. Here it is 2 p.m.
Yeah,
Okay.
I'm at 7 a.m. here, so not too bad. It could have been worse.
Yeah. Let me see.
तो क्या डालते हैं उसको एनडी केबल? अबे चेक तो करने दे, क्या हो गया? नहीं नहीं बता ना, एनडीए केबल बोलते हैं ना, एनडी ए है केबल. एनडीआई होती है एनडीआई।
एनडीआई not only but the spatial organization.
So I think we need to promote these attendees too, because they will be presenting.
कनिया, ये कैसे होता है यार कनिया इंस्टॉल एनडीआई केबल?
तो भाई क्यों नहीं बताता भाई एनडीआई केबल?
वो बिजी है यार।
यहाँ पे जो आए वो फोन वाला पहले चेक करना भी बैलेंस हो गया तो पता मुझे स्पीकर की अब एजेंडा नहीं तो क्या करूं?
एजेंडा है ही नहीं। नहीं पहले इंस्टॉल करना पड़ेगा ना।
तो इंस्टॉल नहीं किए?
मैं वही कह रहा हूँ ना कैसे करना होगा। मैंने वो डिवाइस डाला अपने पेन ड्राइव से।
ड्राइवर दे दो भाई वो
डाला ना मैंने यार। मेरी
कहाँ डाला हुआ है?
डेस्कटॉप पे ही है नीचे करके। ये है ना सेटअप। अरे यार अब 3 महीने में अब तो ये यहाँ तक तो मेरे को भी समझ आ रहा है। फिर ये कह रहा है ओके करो, यहाँ एक खुल रहा है। अब इसमें से कुछ और चीज मांगता है वो इंस्टॉल करने के लिए, तो दिखाई नहीं रहा यार। चीज दिखाता वो बीबी केबल क्या बोलते हैं, बीबी केबल। हाँ हो नहीं रहा यार ये।
Just a short question.
Yes, sir.
Okay. Then I would try to briefly open the name It was also almost called title, which is observed the regular observation of the vertical view. Satellite mission.
यार यहाँ तक आ रहा है यार, उसके बाद नहीं समझ आ रहा।
अभी स्टार्ट नहीं हुआ ना?
नहीं, अभी तो टाइम है, 10 मिनट पड़ेगा। ये इंस्टॉल नहीं हो रहा ना, इंस्टॉल दिखा नहीं रहा यार। ये कहीं से बीपी केवल कुछ कैसे करते हैं फिर।
Good morning, folks.
They operate very similar to GPS. That's also the horizontal electron pointing can be derived from the data measurements. And because the distance between the rays satellite pair is only around is
हट जाएगा, कंपनी वाला प्रिंट भी नहीं देगा, आप लोग को तो दे भी देता है।
हमें कहाँ मिल रही है भाई, 3 साल हो गए।
the horizontal electron density. So even though the satellites do not provide magnitude,
ये समझ नहीं आ रहा है। अरे यार रन एडमिनिस्ट्रेशन भी कर रहे हैं।
we can also provide at least
हाँ
approximation
इंस्टॉल
of the absolute electron density.
यही है। ओके हो गया, हो गया, हो गया। ओके
By having a full frequency,
आ गया,
yes.
आ गया।
Now, okay, first of all, going to the left side,
ये रहा।
if we have all
रन
the
एडमिनिस्ट्रेशन करना पड़ता है, वही बोल रहे थे दिमाग में।
cover almost all times,
बस ये लिमिक्स को लिमिक्स को ना
जूम का भी करना पड़ेगा।
जूम को भी करना पड़ेगा। भाई बेल वेल दे दो, बजानी है।
टाइमर लगाना पड़ेगा।
नहीं बजाए। हाँ कर दे।
ठीक है, तो भी कर दो।
हाँ कौन आ गई?
चलो मैं हो गया। अरे उनका यूआरएल खुलवा दो यार। सबको लिख के दे रखा है क्वेश्चन का। वो टूल है, कैसे टाइप करेंगे वो? यूआरएल तो वो टाइप करते हैं तो 2 घंटे लगा देंगे।
which is also connected to the first frequency. For the absolute calibration of the electron density, we make use of radar stations. And in case radar stations are not available, they each connect based out with fallback calibration against the show you a few preliminary results. On the right side, there is the average electron density for 200 in magnetic neutral time and magnetic latitude. On the right side, there is the electron density from the main. See that both the amplitude is completely different. Also, the rotation of the peak is also much more near in set, which is not the case for the moon. This is the lack of privilege in the management. Another unique opportunity for simple brain scholars is to study regular phenomena, for example, equatorial plasma extinctions, which are displayed here in the bottom three figures. On the left side, we have the large DC measurements from the GPS. They look back rather similar, however, there's no variation. On the right, there are specifically differences between grade A and grade B plotted. And top of this figure is the electron density event measurement. You may nicely see the match between the fluctuations in the electron density and the scatter in GPS derived. And since my time is running out, I'd like to welcome questions.
Hare. Hare.
Hello, everyone. I hope you can hear me.
Yes, we can.
Okay, thank you. So, welcome to our session on recent advances in observation and modeling of the ring current system. And my name is Vanya Jordanova from Los Alamos National Laboratory. I will be chairing this session together with Yichun Yu from Beihang University, China. And let's see. Our first talk that is scheduled here is by Dr. Lynn Kissler from the University of New Hampshire, but I do not see her online. Maybe let's see, we can wait few minutes. And if she doesn't come online in the next few minutes, then we can probably start with our second talk, and then we will come back to her talk when she joins us. What do you guys think?
Sure.
I wonder if she have uploaded the recorded talk.
I don't know. I don't have access to recorded talks.
Yeah, me neither.
It seems reasonable to come back to it.
So does the moderator have access to recorded talks? Could you check if Lynn Kissler has uploaded her talk?
Does somebody have her phone number?
No, but I could shoot her an email if she sees it.
Yeah, why don't you try doing that and see if she replies? Maybe she's trying to join and has problems.
Hello.
Yes?
We share the PPT and your talk for everyone.
Pardon?
And share screens are allowed for every participant.
I could not understand what you said. Okay, so why don't we start with the second talk in our session? So Dr. Shun Imajo from Japan.
I'm ready to talk.
Okay, so the title, Meridional Distribution of Ring Current Ion and Pressure-Driven Currents in the Night Side Inner Magnetosphere from Arase Observations. So why don't we start with your talk then? Please share your screen.
Now I'm sharing screen.
Yes, we can see it.
Okay.
Oh.
Can I start?
Yes, please.
Okay. Thank you, Jadanova-san. Today, I'll talk about the meridional distribution of ring current ions and pressure-driven current in the inner magnetosphere. This study is already published in JGI Space Physics. I did not talk about all details due to the limited presentation time. So see this paper if you need more detail. As you recognize, spatial distribution of ring current plasma have a significant impact on studies of various phenomena in the inner magnetosphere. Previous studies have reported L and MLT distribution of plasma parameter near the magnetic equatorial plane using AMPT-CCE and recent RBC satellite. AMPT-CCE and RBC had low inclination orbit, and their magnetic latitude were within 20 degrees. So there was little information available on plasma parameter in the inner magnetosphere at magnetic latitude higher than 20 degrees. Also, the magnetic latitude of medium Earth orbit satellite can vary with orbit to orbit. This is an example of RBSP-B satellite orbit. There is about 20-degree differences in successive orbit. Therefore, how the magnetic latitude of satellite affects the measured plasma parameter is an important issue for the study of temporal evolution of magnetic storms. Because the Arashi satellite, which is used in this study, has a moderate inclination of 31 degrees, it covers a magnetic latitude range up to 40 degrees and a radial distance up to 6 RE. In our study, we established average Meridian distribution of proton plasma and pressure-driven current, including in the region above the 20 degrees. Because based on the observational result, we demonstrate how important the magnetic latitude actually for interpretation of temporal evolution of ring current plasma. The Earth satellite have a medium Earth orbit with a unique inclination of 31 degrees. Magnetic field data with spin period resolution were obtained by MGF. The plasma pressure was calculated from proton flux data with the energy range of 10 to 180 keV measured by MEPI. We use the data from when Arashi was located on the night side of 20 to 4-hour magnetic local time during this period. In the current study, we analyze the data from moderately disturbed time defined by symmetry star between -80 and -40 nanotesla. Median distribution were given by averaging the value in each spatial beam. We use the two types of beam. The meridional plane in the cylindrical solar magnetic coordinate, and the magnetic latitude distribution as a function of L stars. Now I show the result. These are the distribution of perpendicular and parallel plasma pressure. There's a peak at around 4.3 RE on the magnetic equator. Below two panels shows the perpendicular and parallel plasma pressure as a function of magnetic latitude for lower L stars and higher L stars. The plasma pressure decreases with increasing magnetic latitude. For example, L stars at 4, plasma pressure at 30 to 4 degrees was only 30% of that near the magnetic equator. The rate of decrease tend to be large at the lower L stars. We will discuss later the decreasing rate using our model estimation of the field-aligned particle distribution. For all L stars, the perpendicular pressure drawn by solid line is larger than that of the parallel pressure, even at a higher latitude. This is a distribution of plasma pressure anisotropy. The anisotropy is defined in this equation, and the positive value means larger perpendicular pressure. The plasma anisotropy was positive in the entire meridional plane. The pressure anisotropy at the magnetic equator decreases with increase in the radial distance, which is consistent with previous study. This feature was also shown in off-equatorial region. The pressure anisotropy strongly depends on the radial distance. magnetic latitude distribution in this figure indicates that pressure anisotropy was not changed largely with magnetic latitude. This is a distribution of perpendicular and parallel plasma beta. Plasma beta drastically increase with increasing radial distance, which is consistent with previous study at the magnetic equator. Plasma beta drastically decreased with increasing magnetic latitude. Their magnitude at 30 to 40 degrees was 1 or 2 orders smaller than that at the magnetic equator. This is due to decreasing plasma pressure and increase in magnetic strength with increasing magnetic latitude. This is a distribution of pressure-driven azimuthal current derived from averaged pressure and magnetic field distribution by this equation. Pressure gradient current flows westward outside the pressure peak and eastward in the inside the pressure peak. Westward current was stronger than the eastward current. A large portion of pressure gradient current was distributed within 20 degrees. Curvature current flows eastward. Contrary to the pressure gradient current, the curvature current is limited near the equator within 10 degrees. A total pressure-driven current almost reflects the pattern of pressure gradient current because of smaller curvature current. The main part of the total pressure-driven current was also distributed within 20 degrees. So which is in agreement with current derived from the curve of the averaged magnetic field. Here we discuss the rate of the decrease in plasma pressure with magnetic latitude. We consider a simple condition that particles are trapped in the same flux tube and the particle distribution is in static equilibrium. Parker demonstrated that the distribution function f at the location s on the same field line can be expressed by this equation. Based on his theory, we obtain the simple model for field line pressure distribution, like this. These are comparisons with plasma pressure derived from both measurement and theory for each L stars. The black line shows measured plasma pressure normalized by the averaged value at the magnetic equator. The measured anisotropy is displayed at the top of each panel. The magnetic latitude dependence of the measured pressure and averaged anisotropy roughly agree with the theory at L stars between 3.5 and 5.5. However, the averaged pressure decreased more steeply than the theoretical result at L equal 2.5, 3, and 6. The latitudinal dependence of the plasma pressure and plasma beta is not negligible, as shown by our statistical result. We show a good example of how the plasma pressure and plasma beta depend on the magnetic latitude in successive orbit. This example is in the rate recovery phase from 30 September to 3 October 2017. Although CMH star was relatively constant, the plasma pressure and plasma beta is significantly changed from orbit to orbit. These changes correspond to the changes in the magnetic latitude. There is a one-to-one correspondence between increase in the peak, increases the value of the peak of the magnetic pressure and decrease in the magnetic latitude. the plasma beta was affected more, and the order of magnitude differed from orbit to orbit, depending on magnetic latitude. Therefore, one should be careful not to consider variation due to latitudinal difference as a temporal evolution when examining the L-star dependence of plasma pressure in successive orbit. We have shown the average median distribution of proton plasma parameter and pressure-driven current in the night side in the magnetosphere using magnetic and particle observation by the Ara satellite. We found the latitudinal variation are significant. We confirmed the Packard theory of Hilda particle distribution is roughly consistent with observation for L stars from 3.5 to 5.5. Based on the result, we have two suggestions. The first is the latitudinal the variation of plasma parameter and pressure-driven current are not negligible. Second, one should be careful not to consider variations due to latitudinal difference as a temporal evolution when examining L-star distribution of successive orbit. That's all. Thank you for your attention.
Thank you. So very, very interesting talk. Are there any questions?
Xiang, I have a question. Very interesting work. You just showed some perpendicular currents that are driven from the pressure gradient. And do you ever check the parallel current?
We can derive the parallel current from pressure distribution.
Yeah, some currents, the parallel currents could be also driven by pressure gradient.
Yes.
Like a region 2 field line current.
Yeah, so if we take the divergence of perpendicular current, we can derive the field line current, but we only the one slice of the median distribution. We cannot take a median distribution for each magnetic local time. So we averaged all magnetic local time data due to the coverage of data.
Yeah.
So if we have enough coverage of data, we can derive the field line current from pressure distribution.
Yeah, that would be interesting. Yeah.
Thank you.
Thank you.
So could you elaborate more on what is the cause for this latitudinal dependence of the pressure?
The cause? We just to make a simple explanation. So the I would say only the smaller pitch angle particle can reach the higher latitude, but the pitch angle distribution around the particle with the pitch angle distribution around 90 and only in the near the equatorial plane. So that's why the flux of the higher latitude region is smaller.
Okay.
Yeah, this is just a simple explanation. So his model is the simplest one.
Okay. Thank you. Any other questions? Okay, so if not, let's continue. Our next talk is given by Martina Hulidou from the Johns Hopkins University from the USA. So Martina, please go ahead.
Thank you. Okay, you guys can see the screen all right?
Yeah.
Yeah.
Yes, thank you. Thank you very much for inviting me to give this talk. I want to talk a little bit about key observations or the lack thereof to guide ring current modeling. And this is, of course, my personal opinion, guided though from papers that have published already. Oops. Okay. So first of all, I wanted to identify the ring. Oops. Sorry. The ring current modeling challenges as I see them. One major challenge for any ring current model is to represent the electric and magnetic field self-consistently. In order to do that, they need to get the pressure distribution right, which means that they need to have to identify what kind of particles are transported into the inner magnetosphere, where are they coming from, what are their energies, and how do they get to the inner magnetosphere. And the second part for the magnetosphere-ionosphere coupling and the self-consistent electric fields is very important to get the conductance right, which has been a problem for decades now. So you need to identify as best as possible the electron precipitation to the ionosphere. And of course, once you get the source there and you have the ring current buildup, another major issue is to quantify the relative loss of different loss mechanisms to the ring current. So here I want to summarize a few observations from the Van Allen probes mission. It's a mission, it's over, unfortunately. Van Allen probes scanned the inner magnetosphere from 2012 to 2019. There were two spacecraft, highly elliptical orbits, with apogee about 6 Earth radii. So they were really into the radiation belt ring current region. So I will focus on observations from this mission, and also I will focus this talk on the sources of the ring current. So more or less the first part, the black letters here, not so much the gray areas. So traditionally, I think with ring current models, once they were getting their goal was to predict the DST index. And once they were getting the DST index more or less correct, they were declaring success. I think through the years, this has been shown that it's inadequate. Of course, we have the favorite DPS relationship that estimates the energy stored in the ring current using the magnetic field perturbation on the Earth's surface based upon the decrease of the DST index. However, there have been identified several caveats. For once, the DST index is significantly affected by the tail current. And for another reason, Bela et al. In 2005 showed the existence of a substantial ring current even during low geomagnetic activity when DST index is close to 0. So those problems had identified in the past. However, I want to emphasize a couple of studies here where they showed that the DST increase and decrease during the geomagnetic storm doesn't tell you the state of the inner magnetosphere, like what kind of particles are there, how long they're staying there. It's not representative of the populations that build up the ring current and how they get lost. For example, this is a study by Gulido et al. In 2016. Where it showed that lower energy protons below 80 keV correlate well with DST index. You see right here, these are partial pressure contributed by low energy particles. While as you go to higher energies, you start seeing not only that there is no much correlation with DST index, but also the very high energies, here is the 220 kV, you see anti-correlation. Also, KCAM 2018 showed a very interesting three-step buildup of the ring current population during the March 17, 2015 storm, where in the first two steps you have pretty much the pre-existing cold plasma sheet population penetrating into the inner magnetosphere down to L to 2.5, and it's only later during the storm around the minimum DST that you start having contributing energies above 100 kV at L equal 3. And those energies making a significant contribution. So he interpreted that as penetration of a hot, dense plasma sheet population generated during the course of impulsive magnetotail dynamics during the storm. So it's evident from these studies that the DST doesn't capture really the dynamics of the particles themselves. Another point I wanted to make about storm time ring current dynamics is, of course, the composition. And the Van Allen probe's mission lasted long enough so that we cover maximum and minimum of a full solar cycle. And I also refer to this very nice study by Muikis et al. In 2019, where they did a comprehensive analysis of ring current during CME and CIR storms. And they found that during CME storms, in general, you get higher pressures in the ring current. But if you see here, these pressures, during CIR and CME storms, you don't have much difference in the proton populations. However, you do get a significant enhancement of O+ in the case of CME storms. So Muikis et al. Interpreted this result as having the fact that you have stronger ring current during CME storms must be because of more efficient O+ outflow. And the third part I wanted to talk about, and this has been, especially the last decade, the center of debate in the inner magnetosphere dynamics, is the effect of mesoscale transport on ring current buildup. So in the tail, for many years, it has been observed that transport and energization occurs largely in the form of discrete activations such as substorms or bursty bulk flows. Here I'm showing an example of a paper from Runov et al. 2009 with Themis data, where he shows this kind of injections and depolarizations in the tail. However, this is just an example. These kind of studies go back to the 90s with Vasilis Angelopoulos. But the interesting thing is that during the Van Allen probe era, we also saw a lot of these injections penetrating to the inner magnetosphere. And in fact, the study by Gulido et al. In 2014 tried to quantify the effect of these injections to the ring current buildup. They found that they provided a major contribution of 30%. However, I should say that when I conducted that study, I was making a lot of assumptions about the size of these injections, for example, as they come in, or their frequency. Because of course, when you have one, even two satellites in the inner magnetosphere is not enough, and I will talk about that later. So anyway, evidence exists that probably there is an effect in the inner magnetosphere, but we are not sure, and it has not been confirmed observationally. Now we go to models. They seem to be a little bit further ahead than observations in a sense that they can make different assumptions. They have high resolution models these days, MHD models and ring current models. So there are two kinds of efforts that are happening in parallel. On the one hand, you have inner magnetospheric models like, I have an example here, the RCME. where they have self-consistent electric and magnetic field throughout the storm. They do include the appropriate drift physics in the inner magnetosphere, so both magnetic drift and electric drift. However, they have no solar wind coupling. They're strongly affected by what kind of boundary conditions they put at their outer boundary. And they also have slow flow approximation, which is not always ideal for the tail assumptions, for example, and these bursty bulk flows when they come in. Nonetheless, there are a couple of studies by Yang et al. In 2015 and 2016, where they showed that bubbles contribute an average of 61% to the plasma energy inside geosynchronous orbit for storms with DST smaller than 70 nanotesla. And of course, in his follow-up study, he showed that although these bubble injections are the main source of the ring current, quasi-steady convective models with their boundaries set at geosynchronous orbit are able to predict the large-scale buildup of the ring current pressure distribution, given the appropriate condition along that boundary, which reflect integrated effect of injections. So that actually kind of solved the conundrum. Okay, if you really need injections to build up the ring current, how come these traditional ring current models for decades have been predicting the ring current okay? It really matters whether you put the right boundary conditions at 6 at geosynchronous orbit, for example. And then the other efforts are to have a global magnetospheric model where you have the solar wind coupling, tail dynamics, appropriate drift physics in the inner magnetosphere by maybe coupling inner magnetospheric models with MHD models. However, still in these efforts, they put test particle codes. This is an example by Sorathia et al., a paper that he recently submitted. So they don't have self-consistent magnetic field, but yet they do find that these kinds of bubbles contribute to the ring current. So I think that it's a major challenge for the future models to couple the transition region from the tail to the inner magnetosphere properly so that we can more accurately predict the ring current and its dynamics. And talking about injections, I want to just mention a couple of studies, actually a series of studies that have been done with Van Allen probes data, again in the inner magnetosphere, by Motoba et al. He showed that the ion flux ratios before and after dipolarization in the inner magnetosphere increase or decrease if you look at different energy channels, which is very, very similar to what's happening in the tail. So this is an indication that these are probably bubbles that are penetrating from the tail all the way to the inner magnetosphere, since they have the same properties. And also by analysis of pitch angle distributions, he kind of inferred certain type of accelerations along these injections in the inner magnetosphere. And going to modeling and also different studies of injections in the inner magnetosphere, both models and observations show that ion acceleration on injection fronts depends on the ion charge state. So more than the mass. So doubly ionized ions reach twice the peak energy of singly ionized ions, suggesting that the peak energy is determined by the finite injection width. So these are all kind of properties that of injections that have been observationally established, and they're a good checkpoint for any model that has injection into build up in their code, and they can simulate this kind of activities. However, there is a major challenge observationally to assess the global consequence of mesoscale transport. And that is because for years we have had either in situ measurements where even if you have 16 satellites in this particular paper by Turner et al. In 2017, in the inner magnetosphere, it's very hard to get the global properties of injection in sense how the sizes and how they evolve from the outer to the inner magnetosphere. It's very hard to do that with in situ measurements. And on the other hand, from global ENA measurements, remote sensing type of ring current, for years, I think the temporal and spatial resolution has been limited. Only recently, Kisi et al. In 2021 published a paper using twins data and really pushing the instrument capabilities with 2-minute type of cadence with creating temperature maps, where she started seeing some evidence of injections in the inner magnetosphere, in the tail, and started comparing with in situ data from MMS. So just to close a little bit my idea on the measurements that we are lacking, and by no means these are the only measurements we're lacking. This is an example, and it's close to my heart. I think that in order to understand under what conditions mesoscale processes in the coupled magnetosphere-ionosphere system become geoeffective, we need to observe the global system in mesoscale resolution. And ideally, we would like to combine both imaging and in situ measurements. And with imaging that we have, through these decades, the instruments have been evolved, so we can get higher sensitivity, which means higher temporal resolution and higher spatial resolution. So maybe we can capture the dynamic of these injections with imagers. Finally, I just want to advertise a new chapter we have. There is going to be a whole new book of the Van Allen Probe's mission, where all the instrument teams identify their calibration, in-flight calibration properties, the new stuff that they did during the mission, and also identify the major science findings. And here I just want to advertise the RB-SPICE chapter, in-flight calibrations, lessons learned and scientific advances. It has been submitted to Space Science Reviews. And I will end with this one. Thank you.
Thank you, Martina. Are there any questions for Martina?
I'd like to ask a question.
Yes.
Sure.
Thanks, Vanya. So Martina, I'm not sure I understood you correctly. You were talking about the disconnect between the inner magnetosphere codes and the MHD codes. Mm-hmm. And were you saying that the inner magnetosphere codes are compensating for the missing injections by twiddling their boundary conditions?
Right, right. So that's the only thing they can do. So let me project this again. So the good thing with inner magnetospheric models is they can put whatever they want in the outer boundary, right? They can force bubbles at the outer boundary and see how it moves forward and how much it contributes to the ring current. The interesting thing with inner magnetospheric models, if they have self-consistent electric and magnetic field, if they don't put this kind of boundary conditions at their, let's say, 15ary, I'm not talking about having the boundary at geosynchronous, but if you want to start all the way from the tail, if you don't put some sort of depleted flux tube conditions, that's how they call them, you cannot actually push particles into the ring current. So for this kind of models, it's essential to have this type of boundary conditions to create ring current. But yes, they're very dependent on their boundary conditions. And also, they put these bubbles there, but there is also the criticism that because these are models of slow flow approximation.
Yeah, that part I understood. That
yeah,
you're also missing that. Just for the record, as a modeling person, I'll say that you can't just put whatever you want. People always say in the models, oh, you can just get whatever you want. You can never just get whatever you want. There's a lot of physics.
So
constraints on
I
these things.
shouldn't, actually, I misspoke. I shouldn't say what, you know, for this study in particular, Jiang, he did put boundary conditions based on observations, statistical observations at these distances, what kind of properties you would see in injections or bubbles, you know, what kind of density depletions, temperatures, and this kind of thing. So it's not exactly whatever they want. But it's interesting in the very first papers by, like in 2004 and stuff, they really were trying to make experiments. Okay, what if we put this? Can I have ring current? Because if I have just constant boundary conditions, I cannot build the ring current. No, not from 15 RE anyway.
Interesting, thank you.
Yeah.
Oh, hello, Maria. Hello, I'm Marina.
Yeah.
Yeah, so can you hear me? Yeah, I'm Bimbi. I have a very short question for you. In your talk, you said, during CME, the oxygen ion, the contribution can be more just mean, higher just during the IR, just for the pressure. So what may be the reason for that?
For the oxygen?
Yeah.
I don't know. Actually, I don't think people know. This is still under debate. And if we're talking about observations of the future, trying to identify where in ionosphere you will have outflow and under what conditions, I think this is also another major unknown. So this study also only showed that under CMEs, you have more oxygen. How do you get it? There are only theories. Maybe you have, as the CME comes, I think maybe you have more CASP outflow. That's one theory. But in general, I don't think there is an established reasoning why you have more oxygen during CME storms.
Okay, thank you. Yeah, thanks.
Okay, thank you. So let's proceed to our next talk. It will be given by Jian Yang from Southern University of Science and Technology of China. Please go ahead.
Hello, can you hear me?
Yes.
Okay, thank you, Vanya. And can you see my PowerPoint?
No.
No.
Not yet, but maybe.
So you open your file, and second one for last one, share screen.
Okay. Can you see my screen now?
Yes.
Okay. Thank you. Hello, everyone. This is Jian Yang from Southern University of Science and Technology. First of all, I would like to thank the conveners for the invitation, and I hope everyone are doing well in your area. So my talk today will focus on the using the Rice convection model to explain some of these ionospheric signatures related to bubble injections. So first, I will introduce the concept of the bubbles, and then I will update with you about our improved Rice convection model, which is a little bit different from what Martina just mentioned. And then I will show you several examples of what we have done with this new improved model. As you know, in the early 1990s, in the central plasma sheet, they observed the discovery of the Burstibach flows. And about the same time, Pontius and Wolf proposed this theoretical picture of bubbles And in our view, the bubbles and the BBF, they are identical, one from observational point of view, one from theoretical point of view. And the bubbles are defined as these low flux tube entropy bubbles, which has lower PV gammas than their labels. So because of the interchange instability, they will move fast in the earthward direction. Okay. So typically, when one bubble travels through the spacecraft, we will see faster flow, we will see dipolarization, and also the plasma pressure will be reduced. And also we can estimate this low PV253. When this bubble moves earthward, theoretically it should stop at the location where its PV253 is equal to the background. However, the situation can be more complicated because it can oscillate around its philo equilibrium position, and then it may merge into the background due to the energy-dependent gradient curvature drift. The most intuitive way to create a bubble is by the magnetic reconnection, because it will essentially cut this long flux tube into a shorter one and inject a lot of plasma into the tail. So it has a much smaller mass per unit magnetic flux for this flux tube. So it has a smaller PV253. In terms of the ionosphere, we have known for many, many years that when this bubble or BBF travels earthward, it will have the streamer in the ionosphere, because on the western edge of this bubble, it will have enhanced upward Brooklyn current, which contains a lot of electron precipitations. So in the RCM, it has multiple species with isotropic distribution function. So we can calculate its kinetic drift passes in equal speed and gradient curvature drift. And now the RCM is improved by including not only the pressure gradient related Brooklyn current, but also the inertial related Brooklyn current. And it also coupled in two-way with the MHD code. Therefore, it is now appropriate to model faster flows using the Rice convection model. To model the bubble injections, what we usually do is to reduce the distribution function along a sector of the tailward boundary. So when the bubble is emerged on the boundary, it will move earthward inside the simulation in the self-consistent electric field and the magnetic field. To look at the aurora, we also calculate this synthetic aurora by using the electron precipitation energy with an augmentation by the upward Brooklyn current. Okay. So on the left, I show you the Rice convection model simulation of a one bubble injection. So you can see this low entropy bubble is injected, and you can see the magnetic field dipolarization. In the meantime, with the bubble injected into the inside the geosynchronous orbit, you can see there's a strong enhanced partial ring current there. And on the right, that's a simulation of many bubble injections during a storm main phase. And you can see this PV253 distribution along the x-axis. And you can see this black line when each time when the bubble is introduced inside the simulation, it will move earthward. And in the inner megasphere, PV253 is gradually increasing. And because it's inner megasphere, so we can safely assume that the flux volume V here does not change, and therefore increasing PV253 is actually means the increase of plasma pressure. So here they will have a strong plasma pressure there, and we can estimate the DST index here as about minus 186 nanotesla. And now let's switch to the ionosphere. The first thing I want to discuss is about the westward traveling surge during subsequent expansion phase, which was discovered by Asksoff in 1960s. So it is a aurora, a bulge-like structure here, which moves earthward, moves westward. And there are already a lot of discussion about its ionospheric dynamics. But to us, we still think the megaspheric counterpart of the WTS, the westward traveling surge, is still not clear. So here we use RCM to simulate one typical bubble injection into the inner megasphere. So here on the right bottom, you can see our simulation of this westward traveling surge. And using the self-consistent magnetic field, we can actually identify the boundary of this WTS. And when it mapped to the ionosphere, what's clear to us is that it maps right to the westward edge of this depolarization region, which is also means it maps to the dusk side boundary of the bubble. Therefore, when the bubble is injected to about -10 RE, you can see the westward motion of the bubble due to its gradient curvature drift actually drives the westward expansion of this upward region 1 sense current, which makes the WTS drift westward. And we can also calculate how fast the WTS moves in the ionosphere, which is shown in this red curve. And using the simulation, we can also calculate the Fox-tube averaged drift velocity in the megasphere. And you can see these two curves match with each other pretty good, okay, which confirms that the azimuthal propagation of this westward traveling surge is consistent with the drift in the megasphere. Okay, so in our simulation, we think that the megaspheric driver of this westward traveling surge is actually the bubble itself. The second thing we want to discuss is related to the Steve emission, which was discovered in the which was discussed intensively in the recent years. And it is found that the Steve is related to intense seeds. For example, here, this seeds event is about 5,000 meters per second, which is pretty fast. So what we want to do here is look at the megaspheric source of the intense seeds. So we find one particular event to simulate. And in this particular event, you can see there are at least 6 different injections observed by Themis in the near-Earth plasma sheet. So in the RCM, we specify 6 recurrent bubble injections and see what happens in the inner megasphere and also in the ionosphere. So here's the result. You can see during the growth phase, when no bubble is injected, there's no seed. When bubble starts to inject, still no seed at all in the ionosphere. So here black line is the subaurora boundary. Okay, and here now when the recurrent injections occurs, you can see the strong seed invert happened in the near the inner edge of the ring current region. And in the ionosphere, you can see this is a strong westward flow. That is the seed event. And it mapped to the downward region 2 sense current. And this entire seed event lasted more than about 1.5 hours. Okay. So in the detail, you can see when we map the seed into the equatorial plane, you can see clearly the seed is mapped to the inner edge of the ring current. The entire intense seed event is mapped to the region where the pressure is increasing tailward. So that's the inner edge of the partial ring current. And the center of this seed is right at the plasma pores. And it is solely mapped to the downward region 2 field line current. So this tells us the megaspheric source of this seed. It's just at the inner edge of the partial ring current. The third thing we did with this new RCM is to look at this aurora morphology during sawtooth subsonal injections. Here, a sawtooth event is a recurrent subsonal injections during which energetic flux variation at geosynchronous orbit have this sawtooth-like shape. And what we found is during this time, during each of this injection, we can also look at the ionosphere, the aurora have this finger-like morphology. So what we want to do is we want to look at statistically the characteristic of this finger-like aurora and also the magnetospheric driver of the aurora. So first we use the 3-year image FUV data, and we invented this auto detection algorithm to find the multiple narrow and long fingers in the aurora images. So for example, here you can see we find at least 5 of these finger auroras, and here is another time which has also 5 finger-like aurora. And we find that during sawtooth time substorms, there are 83% occurrence rate. During storm time, it decreased to 64%. And during isolated substorms, there is only 18%. So as the geomagnetic activity increases, there is more chance to see this multiple finger-like aurora. And the wavelength of this is averaged about 25 degrees in longitude, which is about 1.5 hours in local time. And so in this study, we find that the sawtooth events not only have temporal periodicity, but also have this spatial periodicity in the aurora morphology. So to explain that, we use this new RCM to model wide bubble injections. So in this particular case, for example, we reduce the entropy for the entire tailward boundary. And what happens is due to the interchange instability, the whole inner edge plasma sheet becomes unstable, and it breaks into multiple injection channels. And for each channel, inside each channel, the magnetic field dipolarized. And in each of the channel, there is an injection of particles. And on the sides of the channel, there are strong broken current associated. So that causes a finger-like aurora. And we also confirm this with by combining the nano spacecraft with images. So the nano spacecraft, for example, in this case, there are 6 different nano spacecraft at different local times, and they observe different particle injections, either dispersionless or dispersive. So we can trace backward with time where these injections occurred. Okay, and here we can find 1, 2, 3, 4, 5 different injection channels. And these channels are roughly consistent with the MLT location of this finger-like aurora. So we find a total of 8 cases which have nearly 1-to-1 co-located channels with this finger-like aurora, which confirms what we studied in the previous slide. That is, each of these finger-like aurora is associated with these injection channels. Okay, so we believe what happens during each of these sawtooth subsonal injection is a wide reduction of PV253, the flux entropy in the entire plasma sheet, and it becomes interchange unstable, and therefore it breaks into multiple interchange channels. And in each channel, it has upward downward pairs of FACs, and the upward FAC causes this finger-like aurora streamer or aurora arc. So it has a spatial quasi-periodic form in the ionosphere. So here is a summary. So we use RCM to do several studies with westward traveling surge, seed event, and also sawtooth substorms. Okay, here I will stop here. Thank you.
Okay, thank you very much. Are there any questions?
I have a question, Jen. So you mentioned this is your new model, which brings up those new features. Have you ever compared it with your old version of model? Do you see the same thing if you use the old model?
Yes, we see basically the same thing. The reason behind this is that these three different things we see is mapped to the relatively the inner magnetosphere, roughly inside the 10 RE. So although we introduce bubble from the tail, but when they comes into 10 RE, their dynamics are, an approximate way to be treated as a slow flow.
Yeah.
So which means that either the old model or our updated model are both suitable to model this kind of events.
Okay.
So how far in the tail do you need to introduce this?
You mean how far from the tail?
Yeah, how far do you have to push your outer boundary?
Well, in our in these new models, typically we put the tailward boundary at about between 15 to 20 RE.
Okay.
Traditionally, in the RCM, when the slow flow assumption is well satisfied, usually we assume it should be like inside the 10 or 8 RE.
Mm-hmm.
Yeah.
How do you deal with the assumption like the closed field line? So if the reconnection happens inside 15 RE, I think it's possible. How do you deal with that condition?
We simply exclude those regions.
Okay.
Okay, thank you. So let's proceed with our next talk. Will be given by Binbin Ni from Wuhan University. Please go ahead.
Okay, thank you, Velia. And let me share my check. So can you see my presentation?
Yes.
Okay, thanks. Okay. Good evening, everyone. So here is Binbin Ni from Wuhan University, China. So first of all, I would like to thank the session conveners who invited me to give this presentation. And also, I hope all of you are very well. Anyway, so the title of my presentation is that identifying EMIC wave driving recurrent proton precipitation through random probes and post-conjugate measurements. So as we know, EMS wave are a very important wave mode in the inner magnetosphere. They are often observed in the frequency range between 0.1 and 5 Hertz, and also at 3 distinct frequency bands, generally the hydrogen band, helium band, and the oxygen band. Also, they are generally left-hand polarized. And also EMS waves are also often observed both by spacecraft in space and also by the ground-based magnetometer, showing, for example, by the left figure and by the right figure. And also you can see the waves are very intense. Generally, they can, with the typical amplitude maybe around 1 nanoTesla. Basically just on the afternoon to mid-light side. So they can cover a very broad L-shell range and also a MLT range. The role of EMS waves are very important in the particle dynamics in the inner magnetosphere. For example, EMS wave plays a crucial role in the efficient loss of random belt relativistic electrons. They are capable leading to the very fast loss of the relative electron, generally above 2 MeV, at the low time scale. For example, on the time scale of hours or lives. For example, based on these figures, the lifetime can be very short if they are interact with the EMS waves. And also this loss of relative electron by EMS waves quite consistent with observations. The last figure just on the bottom, just showing the Van probe A observed the fast loss of 3.4 MeV just on the time scale of several hours. So you can say the loss may be by more than an order of the magnitude. The red panel shows that EMS wave can also drive loss of the reincarnate protons at the same time. The figure shows that the diffusion rate can be very strong at the rate maybe about 10 to minus 4 or 10 to minus 5 per second. This corresponds to the loss time scale maybe around 1 day or several hours. So this means EMS waves are very important, to cause the dynamic variation of the Earth's radiant belt and also the ring current. However, they have very limited direct connection between EMS wave and the ring current proton precipitations. For example, we need simultaneous observation of both the EMS waves and also the ring current proton precipitation at the same time. Very, very, likely, we need them to be magnetically conjuncted so we can collect them together, as shown by this cartoon. So we therefore look for robust conjuncted measurements between Van probes and the lower pulse satellites. Before, we look at the conjunction between Van probes and the pulse satellites. Pulse is the lower Earth orbiting satellites. They have many pulse satellites. They can orbit at the same time. Generally, the particle observation by pulse just come from two detectors. One is nearly parallel to the ambient magnetic field. They are nominally counting. They are nominally marrying precipitated particles, just from the radiant belt or from the ring current. And also they have other detector nearly perpendicular to the ambient magnetic field, counting the trapped particle population. So based on this kind of post detector geometry, we can get the very detailed information of the ring current proton precipitation. So then we defined, a magnetic conjunction between Van probes and the host. One at the near Earth orbiter and the other at the low altitude. The Van probes can provide very good, very high quality wave information, and the pulse sender can provide, the particle observation at the same time. How do we define a magnetic conjunction? We need the difference between the L shell is within 0.5, the difference in magnetic local time within 0.5, and the time observation. I think we mean the time point of the two satellite observation within 15 minutes. So based on this kind of magnetic conjunction, just shown by this cartoon on the right top, we can have the wave observation in the equatorial region. This is basically the source region of the waves. At the same time, we have low altitude from the pulse of we can have the proton precipitation flux information. Based on the pulse observation, they can give us the count rate from precipitated protons and trapped protons. So based on this, in the bottom, we show the basic idea. For example, this kind of the ratio of the precipitated to trapped proton count rate, they are close related to the wave intensity of the excited waves. So this gives us some information, based on the observation of the precipitated to trapped proton count rate, we can infer based on these theoretical equations we can infer the EMSA wave intensity required to produce the precipitation of the protons. At the same time, in the actual region, we have the EMSA wave observed by the Van probe. Then we can compare them together, so we can verify whether or not the wave observed by the Van probes can explain the recurrent proton precipitation observed by the host satellites. So this is the general idea. So we focus on conjunction events between Van probe B and the LOVA 19 on 26 August 2016. The next figure shows the wave observation from the Van probe magnetometer. We can see the very strong, helium band ESH waves observed by the Van probes. Meanwhile, we can see the post-satellite, post 19. We can see the very, very strong enhanced proton precipitation, the panel E and panel F. For example, here, the panel E and panel F shows the precipitated and trapped proton concentrate for 30 to 80 keV protons, and for the 80 to 240 keV protons. We can say during the conjunction events, we see the enhanced activity of EMSA waves, and also we can say the enhanced proton precipitation shown by the blue line. We can say this is the precipitated proton flux. We can say the very, very strong enhanced precipitation concentrate for this recurrent protons. The red panels shows the, we can say they show the details of the location of the two satellites. We try to confirm, these two satellites, during this time period, they are quite magnetically conjuncted. You can say the LCL difference is within 0.3, and the MLT difference within 0.25, and the time observation, the difference between timers is within 15 minutes. So this means it's a very good conjunction for these two satellites. At the same time, we see simultaneous enhancement of both EMSA waves and the recurrent proton precipitation. Then we focus on this specific time period, and then for our methodology, we use the observed precipitated to trapped proton concentrate, the ratio. They try to infer the EMSA waves based on our theoretical analysis, then compare the inferred EMSA wave intensity with the observation to make sure, we can understand the course of the proton precipitation. So we look into more details of the proton flux and the wave information. We can say during this time period, the shadow region, we can say the ratio of the precipitated to trapped proton concentrate can reach around 0.75 for both end channels. Means the lower end channels 30 to 80 keV protons, and also for higher end channels 80 to 240 keV proton channels. We can say the ratio can, during the conjunction period, we can say the ratio can reach around 0.75. This is really quite high. Means the north cone tend to be heavily filled by the precipitated protons. The photo figure shows the Van probe B observed the helium band EMSA wave. So we can see at this time, we can see the rather strong EMSA wave activity enhanced with the average amplitude around 0.7 megatesla. So then we, at the same time, also look at some other activity. Generally, this is a rather weak geomagnetic condition. We can say the activity of other wave mode or rather weak. So we think this wave mode can contribute little to the precipitation of this recurrent protons. Then we use this observed wave frequency spectrum to calculate the proton scattering rate. We use the two wave frequency spectrum. One is the observed frequency spectrum, this given by the Van probes. At the same time, we also use another frequently used by many research. This is the Gaussian frequency spectrum. This means peak around the peak around the 3 Volkswagen gyro frequency. This is normally frequently used by the researcher. So we try to compare if we use different wave frequency spectrum, how this can affect our simulation results. So use different wave frequency spectrum produce large difference in the proton scattering, shown by this color-coded 2D plots of the diffusion rate. This for these two panels, this gave the diffusion rate at the loss cone just as a function of the energy and also as a function of the wave amplitude. This is the wave amplitude of the EMC wave. You can say use a different wave frequency spectrum produce not difference in the proton scattering rate near the actual loss cone. Why we focus on the scattering near loss cone? Because this tend to dominate the loss of the reincarnated proton into loss cone for precipitation into the atmosphere. This kind of difference may then result in variation of wave-induced proton precipitation. And also we can say the proton scattering rate can be reasonably scaled to the square of the wave amplitude in the collinear diffusion region. This means if we calculate the wave-induced scattering rate for the wave by 1 amplitude, we can scale the diffusion rate for some other wave amplitude by the square of the wave amplitude. So this just can reduce a lot of our communication time. So how to use the post-observed trapped to precipitate proton flux to infer the EMC wave intensity. So based on this equation, so this R means the observed precipitation to trapped proton flux, the ratio between them. Then we just assume a couple type energy spectrum for the protons with all this kind of calculation of diffusion rate. Then we can theoretically calculate the ratio of the precipitate to trapped proton count rate or the function of EMC wave amplitude, as shown by these two figures. One for the channel of 30 to 80 kV, another for 80 to 240 kV channel. We can say as a function of EMC wave amplitude, we get the shape of the ratio for these two channels. But these two channels will have the observation for them, the post satellite. So by this interpolation, we can just interpolate to get the corresponding wave amplitude. Then we can infer the wave amplitude based on the observation from the post proton count rate. Then we apply this method to all the conjunction period. This just the slide only for one time point, but during a conjunction period, there may be 20, 30 conjunction time point. So we applied all of this method to the entire conjunction period. Then we infer the EMC wave amplitude. The first we use observed EMC wave frequency spectrum. This panel shows the observation. This shows the volume group B observed EMC waves as a function of time. So this is the realistic observations, this observation. And the panel B shows the model results. You can say we use different channel to infer the EMC wave amplitude. So you can say for the 30 to 80 kV shown by the red curve, using the 80 to 240 kV, just defined by the blue curve. And also we use this color just for the entire two energy channel. We combine these two energy channels together, we get the 30 to 240 kV. While we do this, we will show the reason later. But showing by these two curves, we try to compare the observation with the simulations. How we do the comparison? We get the root mean square EMS wave amplitude during this time period. This is the 15 minutes. It's 15 minutes. So we can say, the instantaneous EMS wave amplitude, changed quite a lot, within a factor of 10. But we try to get the RMS, root mean square EMS wave during this 15-minute period, then compare with the model results. So you can see the average, the compare between this observation. This is the observation. This is shown by the dark, by the dark curve. So you can see they are quite consistent with each other. So this means if we use two different channels to infer the EMC wave intensity, then compare with the observations, they are quite consistent. But we use the 30 to 240 kV get the best fit with observation. We can say the observation shows the root mean square until is 650 line per Tesla. If we use 30 to 240 kV, we get the 60 and 68 per Tesla. So they are quite close with each other. So this we use observe EMS wave frequency spectrum. Then we use another Gaussian frequency spectrum. Why we do this? This means if we want to infer the EMS wave intensity from post observation, generally we don't know the wave spectrum. So we have to use a nominal or just frequently use Gaussian frequency spectrum to do the simulation. So this is the results. We can say if we use the nominal Gaussian frequency spectrum, the results can also be quite consistent with the observation. For example, if we use the 30 to 240 kV proton observation, we can get the inferred wave intensity around 60 to 40 kTesla. Is also quite close with the observations. So this gives us some other information. Even we don't have the very good EMC wave spectrum information from observation, we can still use the nominal Gaussian frequency spectrum to infer the EMC wave intensity using the low altitude post observations. So this is the brief summary. So I don't want to show it, but I want to show some other things. So this gives us not just confirm that for this event, EMC wave, tiny EMC wave play a dominant role in driving the reincarnate proton precipitation, observed by the post-19 of the satellite. It also provides a valuable means to construct the global profile of EMC wave intensity. For example, generally we have very high urban satellites. They are orbiting at very high altitude. They have very long period. So they cannot provide the information, of the waves, the near real time. But if we have the lower altitude satellites, there are many of them, and also they have very short time period, and also they have a very broad L shell coverage, so they can provide us, to convert, through near-time conversion to get the global EMC wave distribution. For example, such a method can also apply to Western mode course. This just, we use the similar method applied to Western mode course. We can get the global distribution, at different L shell, at different MLT range, for the entire 1 month. This is just for 1 month. We can do this for nearly 1 year, 10 years. We'll have the lower urban satellite observation continuous. So that's it. Okay, thank you. Sorry, I just running out of time. Sorry about that.
Yeah, it's okay. Thank you. So, are there any questions?
Bingbing, when you compare your observed EMC wave intensity with your inferred EMC wave intensity, the curve as a function of L shell does not seem very similar, right? I mean, the peak is at different L shells.
Yeah, it's a very, very, very good question, frankly. So that's the that's the reason why we use the root mean square, with amplitude for comparison, because we count exactly, to make sure the shape of the variation of the interiors EMC of intensity, very consistent with observation. So this is just the conjunction period, but you can see this the time range is quite short, only 10 minutes or even only 5 minutes or something. So I think this is okay.
Okay, so the difference is due to actually the not exact location of the two observation points, right? So if they're in the exact conjunctive locations, they maybe have better agreement.
Yes.
I guess.
Yeah, I think you have very, you give a very good question, but based on conjunction, if you try to find conjunction, we have to use different kind of models, magnetic field models. We cannot very sure, what this model can exactly produce, the perfect conjunction. Yeah. I don't know if you understand what I mean. Yeah, we have to use some model. They have some error or uncertainty. So I think we are okay with this kind of uncertainty. Yeah.
Yes. Thank you.
Okay, so now let's have our next talk from Jonathan Krall from the Naval Research Laboratory. So please go ahead. So are you muted? I don't hear you.
Ah, there it is. Okay, sorry. When I went to full screen, I lost my unmute button.
Oh, okay. Yeah, we can hear you now.
Okay. Oops, let me get my. Okay. So I'm talking about the this work I've been doing with Mei-Ching Falk, Joe Huba, and Alex Glosser, where they Mei-Ching and Alex have a code called SIMI, which is an intermagnetosphere code, and it simulates the ring current, comprehensive intermagnetosphere ionosphere code, something like that. And so they did the calculation of ring current, and they gave us information on the heating of Coulomb collisions, of the heating of plastosphere electrons by Coulomb collisions from the ring current. So it was basically energy loss. And they originally just gave us this data, or this computer output in the equatorial plane. And this is the integrated heating in the top row here from SIMI. And what we did a study last year, actually started a couple years ago, came out last year, where we cooked up a function of DST to imitate this ring current heating, and we put it in SAMI3, and we got some output where this is from SAMI3. This is without the heating. This is with the heating. The sun is off to the right, and the green isosurface is a density, is the oxygen density at 100 particles per cubic centimeter. And so there's hardly any oxygen outflow here, but then you get this very strong outflow that sort of resembles an L shell, where L is the McElwain parameter. The yellow contours are electron temperature, and the hottest electron temperature without the ring current heating is on the sun side. But with the ring current heating, the hottest temperature is where the ring current heating is occurring, which is more on the afternoon and night side. So this is in the top row. This is from SAMI3, which is an ionosphere plastosphere model. It simulates the motion of ionosphere and plasma particle or fluids, one fluid for each ion along field lines. And so this is the electron density, and this is during the storm, and you get the storm surge, and then you get a plume. That's sort of typical things that you see if you look at plastosphere simulations and observations, although the observations are messier. And the bottom row is the oxygen density, and we don't get this oxygen shell out here or oxygen torus without the ring current heating. And and when we do profiles, like profiles versus radius of the electron density, which shows the plasma pause here, and the mass density, we get results that are similar to observations where there's the plasma pause and there's the mass density. And the one funny thing about this is that a lot of observations look like this. In this particular case, we only have the mass density outside the plasma pause. But even when you see a curve like this, and you see this jump in the mass density, and you see this jump in the mass density here, this is average mass versus L. At the plasma pause, you get the idea that the oxygen shell or oxygen torus is outside the plasma pause, mostly outside the plasma pause. But in fact, this enhanced average density in here inside the plasma pause is also the oxygen torus. And in fact, in the simulations, this trace comes from the simulation. That's where these traces come from. These are SAMI3. Is that it's actually inside the plasma pause. And if you go back to the earlier papers, back when this was first seen in DE RIMS data, it's the Dynamics Explorer results from the 80s. It's identified as being inside the outer plastosphere. And they also refer to it as torus/shell. This is Horowitz et al. 1986. So so we did this result, and it has a nice result which suggests that ring current heating is causing the oxygen shell. And but one question that came up in our work was that in our paper, we incorrectly stated that the heating was only applied above a certain number of RE altitude. And in fact, it was actually applied along the entire field line. And so that line in the description was a mistake. But we questioned ourselves, should it have been applied along the entire field line? And so the first thing we did was check the effect, because if it's applied, if the heating affects the entire field line, then it's directly affecting the ionosphere. And so this is it's very similar to the published result. It was just using the latest version of the code, which is ever so slightly different. And then the bottom row is the same result, except that we applied the ring current heating only above 1/2 RE altitude. So it misses the ionosphere and misses the topside ionosphere. It just gets the plastosphere. And you can see they're almost identical. So in the simulation, direct heating of the ionosphere is not important. But there is this question because the ionosphere does heat. This is data, this is not from the same event, showing several days. And I think this is from the name of the observatory will come back to me later. Anyway, so before the storm, you get electron temperatures. This is diurnal. The electron temperature has a diurnal variation. And before the storm, the peak temperatures are around 2000 K. And after the storm, they're around 3000 K. So you get a jump of close to 1000. And this is SAMI3. Now the storm peaks at the end of the first day. So these two are kind of before and beginning of the storm, and this is during the storm. And we get a jump of a similar jump of around 1000 K, maybe a little larger. And this is the ion temperature, and the ion temperature jumps by a couple of hundred, and here it jumps by 200 or 300. So we got effects that were similar to observations, but we're not quite sure how much those effects come from conduction of heat along field lines, or how much of it is directly from ring current particles interacting with the ionosphere. And so our next steps, this is work in progress, and our next steps are to take the SIMI, Neijing Falk reports to me that the SIMI simulation does show that the ring current heating penetrates as low as 100 kilometers. And so what I've done is take the SIMI ring current heating output, put it on the SAMI3 grid to analyze heating rates. And one tricky thing about that is the SIMI results are reported as foot point latitude, magnetic field strength, and local time. I translated that into latitude, longitude, and altitude. And so when I did that, this is the SIMI results on the SAMI grid in the equatorial plane, and they look like the plot I showed at the very beginning. So that's nice. I didn't totally screw that up. But this is what it looks like in altitude and latitude. So this is a longitude plane. It's longitude near zero, just so that local time and universal time are about the same. That's just convenient. This is the heating function that we put in SAMI 3 at the same time, and you can see they're similar. And this is something we already saw previously. You get stronger peaks in the ring current heating. The ring current heating is not the smooth function like we put in SAMI 3. But the other thing is that most of the time, the ring current heating is actually above the ionosphere. During the strongest part of the storm, it does reach down to the ionosphere. So, you know, as Mei-Ching reported to me, it does get down below 100 kilometers, but it doesn't do it all the time. And so the effect of this is something we're still trying to get a better handle on. And of course, you can see that the shape is somewhat different. And I'm not sure how important that is too. So this is kind of as far as we've gotten so far. The results suggest that the ring current heats the ionosphere, but direct heating of the ionosphere does not produce significant additional outflow, O+ outflow. So that was our initial modeling result, that if we limit the heating to the plastosphere, we get a very similar result to if we heat along the entire field line. But also this question of what's the cause of the heating of the ionosphere, whether or not it's a direct effect or whether it's a conduction effect, we don't have a handle on that yet. And there's more stuff to be learned. This last plot is oxygen, again similar to the heating plot in the previous picture. This is altitude and latitude, and this shows the oxygen torus near midnight. And there's it kind of looks a little more like a torus there because the peak is up here. At this point, it's actually falling in some places and outflowing in other places, because as you get to dawn, the oxygen tends to fall back towards Earth. Anyway, that's as far as I got in terms of this investigation. Like I said, it's a work in progress. These are some references. This one here is the paper I was talking about the observed O+ shell. So I've left time for questions, and thank you.
Thank you. So now we have time for questions.
Yeah, I would like to ask a question, Vanya.
Sure.
Yeah, so Jonathan, in this kind of model, so you're talking about outflow that will happen inside the plasmasphere, correct?
Well, yeah. I mean, it's inside the plasmasphere, it's outside the plasmasphere, it's outflow from the ionosphere.
Okay, so it can. So, what are the L shells that can cover that kind?
It goes all the way up. The model goes all the way up to the poles. So the L shells go out to, you know, way past geosynchronous orbits. We have a boundary condition where we remove, or where we have a very low density above L equals the altitude corresponding to the peak of L equals 9. So somewhere out there, we kind of remove plasma down to 0.1 cc. So that's our boundary condition, 0.1 cc.
Okay. Because I think when I saw your plots, the initial ones, you were showing this shell to be inside the plasmasphere, this oxygen.
Yeah, the oxygen is mostly the peak outflow of oxygen corresponding to the O+ shell is mostly inside the plasma pod.
Okay.
Now, our plasma pod we defined as 100 cc, and I don't know if that's the best definition. Yeah.
Okay.
Yeah, compared with with a lot of the observations, our plasma pod density, in terms of where you look at the profile and see where the density drops sharply, and tends to be at a higher density than observed. So there's
I see.
there's more work to be done in terms of directly comparing modeled observations.
Okay, any other question?
Actually, I have one, Manya. So,
Yeah.
yes, Jonathan, I have a question about the modeling stuff. So how do you couple the two models? How do you integrate the heating into your plasma sphere model? So it is globally or just at the boundary or just at a high latitude?
Well, it's globally, but the first result, the simulations, was kind of a proof of concept. What we did was we cooked up a ring current heating function that looks similar to the output from SIMI, and ran that in SAMI. So we didn't actually couple the models. We just cooked up a function that looked like a SIMI, and it was just a function of DST.
Okay.
Yeah.
I
So
thought
it's
you
kind
have
of
like a have like a two-way coupling. It's not like
we are working on coupling the models. How coupled they will be, it's not clear. We'll probably have one-way coupling to start with. That's Joe Huba and Alex Glosser have been working on that for a while. It's a challenging problem for a variety of reasons.
okay. Thank you.
Okay, any other question for Jonathan? If not, we have a few more minutes, so we can ask people that have posters to say a few words about their posters. So, Masahito Nose, would you like to say something about your poster?
Yes, I think I have a 4 minutes to introduce my poster briefly. Can I share my slide?
I think so.
Okay. So I think you can see my screen.
Yes.
Yes, this is my poster title. So the original poster title was different from this. I have changed slightly, but the content is the same. In this poster, I'm going to report the flux enhancement of the field-aligned low-energy oxygen ions. I called the FAREO that appeared in the inner magnetosphere, and I will discuss a possible source of one plasma cloak and oxygen torus. I should go to this. Okay. So this is a satellite orbit during this event. This event was simultaneously observed by 3 satellites, ARASE, Barnum Probe A, and Barnum Probe B. All of these 3 satellites was located around the midnight, and ARASE was below the geomagnetic equator, but Probe A and Probe B was above the geomagnetic equator. And this is a summary of these 3 satellite observations of field-aligned low-energy oxygen, FAREO. And here is the timeline of this event. At 0524 UT, substorm occurred. And after 3 minutes of the ground substorm signatures, dipolarization were identified by 3 satellites simultaneously. And then at 0533 to 0535, Probe B observed the field-aligned low-energy oxygen ions in both parallel and anti-parallel direction. And its energy decreased from 1 kb to around 10 electron volt. Next, the ARASE observed this FAREO in only the parallel direction. its energy decreased from a few kV down to 100 electron volt. And finally, probe A observed the Fario in the same signature, same characteristics as a probe B. And we performed the numerical calculation to explain these observations. And I don't describe detail of the simulation, but the result of the energy time spectrogram observed by virtual RSA and virtual probe A and virtual probe B are very similar to the actual observations. So we can find these high field line low energy oxygen ions from a few kV to the 100 coulomb in RSA, but to the down to 10 electron volt by virtual probe A and probe B. And I also discuss from the numerical simulation result where this field line low energy oxygen Fario goes in the inner magnetosphere. The left panel shows the distribution of Fario after the launch of the from the ionosphere. And you can see low energy oxygen is distributed in the morning or the dawn sectors because they are very low energy. They do not go to the westward like a ring current, but they drift eastward. And this distribution is very similar to those reported for the one plasma probe was oxygen torus. So we think this field line low energy oxygen come from the ionosphere we called Fario is a possible source of the one plasma probe was oxygen torus. So here is a summary, and I will stop here. And if you have an interest, please come to my poster. Thank you.
Thank you. Let's see, is there a question for the poster?
I have a quick question.
Yes, go ahead.
What's the energy of these cold particles or low energy particles?
I launched the energy from 1 kV to the 10 electron volt from the ionosphere, upper ionosphere, altitude of the 4,000 kilometers.
Okay, so 10 EV.
10 EV, sorry. From 1 kV to 10 EV.
Okay, thank you.
Okay, so let's see. Next, Robert Hazard from Los Alamos National Laboratory. Robert, would you like to share a few words about your poster?
Yes, thank you, Vanya. Can you hear me?
Yes.
Okay, great. I will share my screen and give a few words. With limited time, I will only cover a few of these slides here that you'll see correctly. There we go. This is okay. So the motivation is that we want to, as part of the LWS team with NASA, this is part of Lynn Kistler's and Vanya, your team. We want to use measurements of in situ ion compositions like H+ and O+ for quiet and storm conditions to inform models like RAM-SCB, and we'll use the results to drive boundary conditions for those models. The real task of our work, and it is in progress like some of the others, is to use geocentric insertion orbits like Masahiro also mentioned. We're using RBSP A and B and ERG, ARAZE, and we're only looking at L larger than 5 values. So we're trying really to set the O+, H+ density ratios at those L values. So that's the task, is to figure out what we can see in observations for storm time conditions, how these 3 satellites compare, and is there really a surplus of O+ transported into the ionosphere or from the ionosphere to the magnetosphere, and when does this occur? Now, we picked 2 storms, and again, one is a popular one from September 8th, 2017, where the DST gets all the way down to -140, KP was 8. It's a great storm. The other one is, the second case was from a much lighter storm from March 17th, 2019. The reason we chose these two, and here they are here, the one on the left is the one from September 2017. The one on the right is from March 17th, 2019. The reason we chose these two is because the first storm, the big one, RBSP A and B in red here are sunward and ERG is counter sunward. So these are counterposed in the GSM-XY plane. So we can see possibly we can bound what's happening between sunward and away from sunward with our measurements of NO+ to NH+. For the second storm case, these are more aligned. So we can at least do a comparison to make sure that our instrumentation is measuring the same kinds of things. Now we've only got to so far looking at HOPE or comparing HOPE, which looks at the essentially the slightly different energy ranges from LEPI, from ARASE, but we're also looking at ion energies, or we're looking at ion fluxes, and then I convert those to energies, and then I have to integrate over specific energy bins to make sure they match. So I check 10 EV to 25 keV from both, and I had a lot of help from the ERG and RBSP collaborators on this. And we're also going to compare to the Young et al. Equation down here at the bottom in green, which gives the expectation using old ICE data. Now, as you can see here at the lowest DST on the right, lowest DST, we get high oxygen to H+ ratios, as has been previously observed when DST is lowest. Here is the meat of the results that we've gotten so far, and that is for case one, where they are counter-aligned. The magenta line is essentially the prediction by Young et al. For the first case and second case. For the first case, the ARASE counter sunward matches reasonably well, except for outside the storm range, and we still haven't worked that out yet. And sunward, the RBSP Van Allen probes A and B show a much higher O+ to H+ ratio. And so we will be hopefully coming to a better conclusion soon, looking also at high energies and bounding our equations. The bottom down here is where they're co-aligned and they match much more nicely the Young et al. Observations, which is what we expected and what we were hoping for. Now, again, I guess my time is up, but essentially what we got is that there's definitely outflows where the main phase of the storm occurs, and they seem to coincide with DST minima, which has been observed before. Our O+ to H+ ratio sunward seem to be much higher during the storm phases, and what we still have to work out is outside of the storm range, how LEPI and HOPE compare. And then, so that's really what we're at. And so in the future, we'll be looking at more storms, different energy ranges, and then we'll be applying these to the models because that's the purpose of this. We're not doing it specifically for observations. We're using the observations to limit the models. Are there any questions?
Okay, so is there a quick question for Bob? If not, then the last person I think is Kazushia Samura. Would you like to show a few words about your poster?
Yes, I will share my screen.
Okay.
Can I see my screen? Can you see my screen? Video. Okay. Can you see my screen?
Yes.
Ah, okay. Can I start?
Yes.
Okay. In the poster, I report the observational results of cross-energy coupling from fast magnetic waves to EMIC waves through the cold ion heating inside the plasma sphere. So this is this panel shows the observation of ARASE satellite, and the top panel shows the top line shows the dynamic spectra of wave magnetic energy in spin axis component. And you can see the wave activity in wave activity in around 10 hertz and 2 hertz ranges. And this yellow line shows the proton cyclotron frequency. And second panel shows the wave normal angles. And if we can see here at 10 hertz range, the waves has a wave normal angles is near 90 degrees for 10 hertz wave activities. And also, if we investigate polarization of these waves, these waves has a linearly polarized. So we are concerned that this is magnetosonic waves. And also, if we consider these waves, 2 hertz waves, and the same analysis, we identify these waves as EMIC waves. And simultaneously, the heating of low energy ion is observed. This is the energy time spectrogram of proton energy flux. And you can see the enhancement of low energy ions around, say, 100 dBs. And these ions are perpendicularly heated. So this is a pitch angle plot. So, and this is 90 degrees. So it's clear perpendicular direction heatings. So since we have the event of simultaneous event of MSWs and EMIC as ion heating, we applied wave particle interaction analysis for this event. Wave particle interaction analysis, WPA analysis calculates the inner product of wave electric field and the particle velocity vectors. And so this is basically the energy transfer rate. And if this energy transfer rate is positive, this means that the energy is transferred from waves to particles. And if it is negative, the energy is transferred from particles to waves. So if we apply this analysis for the magnetosonic waves, the result is like this bottom panel. So this bottom panel shows the energy transfer rate. And if we averaging out these values, the value is positive. So this means that the wave energy is transferred to the particles. So particle is heated by waves. And then we also applied same analysis for EMIC waves we observed. And in this time, we got the clear negative enhancement of energy transfer rate. That means that the ions, a part of energy, a part of energy of ions consumed to generate the waves. So in summary, so we identify cross-noise coupling from magnetosonic waves to EMIC waves through ion heating by WPA analysis. And this analysis shows that the MSWs accelerate protons with energy around 100 eV. And also we have observed that proton bound EMICs, and again, the WPA analysis shows that the heated ions contribute to generate EMICs. So at first, we show that the cross energy coupling process by the direct analysis of energy transfer rate based on in-situ measurement. So the first ring-like distribution of ions will excite MSWs, and then MSWs heated up the plasmatic cold ions, and then these ions contribute to excite the EMIC waves. So that's all. Thank you.
Thank you. So I see that also Sandeep Kumar has joined. Sandeep, would you like to say something about your poster?
Yes, ma'am.
Okay, go ahead.
I'll share my screen.
Okay.
So my poster is about a contribution of electron pressure to ring current using RAM simulations and RSA observations. And So we know like mostly ring current consists of ions, and generally during storm time, ring current main contribution is from ions. But electrons have been given very much less attention to the ring current, and there are some studies which shows the contribution of electrons, which is vary from quiet time level to storm time level. Like for example, like especially electrons from 1 to 50 keV energy, they contribute around 1% to the ring current during quiet times, and during active times, this contribution increases to from like 19 to 25%. And some simulation studies have also shown like contribution of electrons from during storm time around 10%. So basically, electrons are having some very small contribution, but this is non-negligible. And in this study, we use this RAM simulation, RAM simulations, and this is basically a code which kinetic model of ring current, three-dimensional. So there are three basic requirements of this model, and we use this plasma fluxes at outer boundary from geosynchronized Los Alamos satellites, and electric field and plasmaspheric calculations we give from this Weimar model. And it also consists of magnetic field, which is fully anisotropic, self-consistent. And this simulation takes account of Low's terms like charge exchange and Missler mode waves and atmospheric coloration. And solving this simulation, we get particle fluxes from 100 eV to 400 kV range, from L shell 2 to 6.5 with pitch angle from 0 to 90 degree. And this is the storm which we studied during this study. So during 8 UT, the main phase of the storm started, and this figure shows the Arase orbit during this particular storm. And we compared the ion fluxes calculated from RAM simulation and Arase, observed by Arase. So we can see here this vertical line shows the main phase onset. So you can see from all panel, like this is proton, this is oxygen, helium, like calculated fluxes and observed fluxes are almost same. And this is the electron fluxes, and RAM simulation calculated and observed. And then we compared the plasma pressure for different energies for Arase and calculated from RAM SCB. So RAM SCB reproduced this plasma pressure very well. And we used ground data from 31 magnetic stations. And this shows the ground data for this particular storm. And then we say the plasma pressure calculated from, integrated from L3 to 6.5. So this shows the MLT variation of this ring current pressure with CMET. And this is the ratio of plasma pressure to the total pressure for each individual ions, like ions and electrons. So we can see like electron pressure was more at dawn sector. Then we checked ground magnetic data at dawn sector from 3 to 8 MLT sector, and the corresponding electron pressure in the magnetosphere. So we can see here that enhanced pressure here has given like magnetic depression at ground. So so this means like electrons contribute to this magnetic ring current at dawn sector. So this is the conclusion, like the electrons from 10 to 50 keV have contributed to the ring current during this storm. And this is, they have no negligible contribution, around 17% to the ring current at dawn sector. So thank you very much. If you have any question, you can ask me, and you can visit my poster.
Thank you. I think we are a little bit over time, so we need to finish this session, but please go to the poster sessions to have more discussion. So thank you all for participating and for the lively discussions. Hope to see you sometime in person in the future. So bye for now.
Thanks, Rania.
Thank you. Thank you, guys.
Bye.
Thanks, Vanya.
Thank you very much.
हो गया ना, यहाँ से देखो तो क्या करोगे ना, यहाँ पे ऑप्शन आता है, अगर खुश नहीं रहोगे ना यहाँ कर दिया।
क्या कह रहे हो?
ले लो यार, अब क्या करते हैं भाई, डबल नहीं हो जाएगी।